Okay, fundamental theorem of calculus part one. Um, Basically, the fundamental theorem of calculus part one is the idea that if you take the derivative of the antiderivative, you should get the function back. Now remember, there's a lot of hiccups when we do that. The key component is there's simply an x here, and that is a constant. A is a constant. Okay, if if that is true, you have your integration is from a constant to an x. You're visualizing you're taking a graph of a function from a to x. That's the area under the curve. Okay, which would be representative of a function f of x. Uh, that's a simplistic view. Uh, However, if in here it's not simply x, well, the derivative of x is 1. So when you take the integral, you get the f function back right here. You get the f function back because the derivative and integral undo each other. But the hiccup is right there. It's a u. It's like a u. It's like the chain rule. Okay, essentially, basically your u, you'll need to do an u tick at the end. Okay, again, notice that there's a constant right here. Okay, we'll show you what happens if they're both functions. If both up here at the top and the bottom of your integral both functions. I'll show you how that works in a little bit. So it's best to illustrate by example. So fundamental theorem of calculus part 1 says if you take the derivative of an integral, what I'm looking for is a constant at the bottom. I have one. Okay, and this is an x. So basically what happens when I see that, I basically simply write cosine x, and I'm done. Because if I went ahead and plugged in the e into the cosine and I took its derivative, it would be a constant. So if you take the derivative of a constant, you get 0. Now here, the second example, again, I'm taking the derivative of an integral. So they should undo each other. However, here I've got the constant at the bottom, which is good, but at the top I have a u. I have a function. It's not just x. In this first example, x is 1, its derivative is 1. That's why we don't have to write it, so it'd be times 1. But here, I have a function. So what I'm going to do is I'm going to go ahead and plug in the u into the function. Plug it into the function right there. And then I'm going to take the derivative of the u. Well, u is x cubed, so this is 3x squared. Now, as always, pay attention to your solution. It does have some simplifying features. You've got a log of something, but it has power. That power can be pulled in front. So this becomes 3 ln x times 3x squared. So the simplest version would be this. Okay, next example here. Notice now I've got the derivative of an integral, but the hiccup is this is a u, but down here I don't have a constant. It's also a u. So how this works is we're going to go ahead and take the integral of the top and integral of the bottom. Remember, we subtract the top minus the bottom. So I'm going to go ahead and plug in the top. Don't forget it's u tick. Here's u. So u tick is 2. Minus, now I'm going to plug in the bottom. It's e to the x, but its derivative is just 1, leaving me with the result of 2e to 2x minus e to the x score. One more example. Again, notice I have the derivative of an integral. The function should remain t squared, but both of these are u values. So plug in the top. So I plugged in the u at the top, took the top, and I plugged it in. Now don't forget the u tick. Derivative of cosine of the u is negative sine x minus. Now I'm going to do the bottom one. Plug it in. times its derivative, producing a hot mess. You can simplify that to negative sine x cosine square x minus cosine x sine square x. And just factoring features and other things we might want to look at, but right now let's just get to the basics here. Some other components of the integral is, again, the question 22, if you look at your book, question 22 says find the y value in terms of an integral. So 22 gives you the derivative. Here's 22. 22 says so if I want to get rid of the derivative and I want simply y, I need to undo the derivative by taking the integral of both sides. Don't forget your dx. So that would be the general form. However, in the question, they provide you what's called an initial position. They tell me that the initial position is y equals 0 when x equals 8. Okay, now I think the best approach is to consider this graphically. Okay, it's saying that the y is 0 when x is 8. Well, if y is this guy, then y has to be the area under the curve. Now, I don't know what that curve looks like. I just need to do something to help me illustrate this. So let's pretend like that's the curve. It really doesn't matter what it looks like. I'm using this to illustrate. What it's saying is when I get to x is 8, here's x is 8, I have all this area right here. This area is 0. Now the question here is we don't know where to end. It doesn't tell me the ending value. So we're going to end it all the way out here at x. So the area up to x, all the way up to x, is this area here, which is 0, plus the area here. So this area here, this region here, is 0. This region is the area from A to x. So the best way to interpret this is y equals the initial value, which is 0, plus the area under the curve from that position, 8, to some value x of e to the t tan t dt. Notice I'm using t's because I have an x here, which means I need a dummy variable inside the function. I know you want me to do another one, so here is question 24. 24 provides you with the information dy over dx equals the square root of 3 minus cosine x. And they give you the initial condition that the area under the curve y equals 4 when x equals negative 3. So the first thing I'm going to do is I'm going to get rid of the derivative by taking the antiderivative. Easy enough. But that's a very general form. We don't have any specifics. Here I am given that specific information. It's telling me that the area under this curve, I don't know what it looks like. I really don't care. But I know the area up to x is negative 3. Sorry, I put the negative 3 in the wrong place. To negative 3. The area up to, all this area up to negative 3, this area is 4. But this is this is a function, so I need to go all the way out to some value x. So I currently have now the area is 4 plus the area under this curve from -3 to some value x. We don't know. So y equals, the initial value is 4, so 4 plus the area under the curve from -3 to x. And again, we have 3 minus cosine x, but I'm going to use t because I have the x value located right here. And please don't forget your dt. So this is an equation because it has x's in it and y's, but it's in terms of an integral because the original function, the only information we're given was the derivative. Okay. On to 2. Now this is the one we use a lot. We use this a lot more than anything else. Here, we start with the function f. Typically underneath the integral is a derivative because the integral of a derivative undoes each other, giving you the ft. But here, since we don't have a derivative, I'm going to give it a different name. I'm going to call it capital F. Okay? Which means that the derivative of the capital F has to be that f of x. Again, because we want underneath this here guy, right underneath here, I want this to be a derivative, which makes this the antiderivative value. Okay? So 32. And this is where we're going to get into a lot of these things, and we've already seen it, so hopefully we're somewhat ready. 32 gives you the function, the integral from -2 to -1 of the function 2 over x squared dx. Okay, so basically what we're going to do is we're going to do the antiderivative here. But before I do that, I want to pull the constant out 2, and I'm going to put that as a power so I can do the anti. So equals 2. Now I can do the anti. The anti is you add 1 to the power, so I did, and then you divide by that power. Put your bounds, and keep that 2 in front because it needs to be there. It's a constant factor, so it just hangs. So equals. Now I'm going to simplify this because it's got this -1 in here. I don't want it. It's a constant. I'm going to pull it out. So I've got -2 box 1 over x, because I'm evaluating. I want the negative exponents, which gives me that. Now plug in the top. Minus plug in the bottom. And you spit out a beautiful answer of, I don't know, -2 times -1/2 is 1. All right, another example. Let's do number 40. 40 is got some algebra issues, and let's walk through this. Integral of 0 to 4, 1 minus square root of u, square root of u, du. The issue, clearly you can see this is not, this function is not something I can do an antiderivative. It's a hot mess. So what I'm going to do is I'm going to mess this thing all up. 1/4 plus 2/4 equals 1 plus 2/4. So what I'm going to do is basically I'm going to convert it to 2 separate fractions. I'm going to take this guy and convert it to 2 single fractions. So let's get rid of this here and let's work that out. So I get the integral from 0 to 4 of 1 over square root of u minus square root of u over square root of u du, which equals, now I can separate these integrals if I'd like. because it's subtraction. So I'm going to create 2. And notice how nice this is. That's just equal to 1, so it gives me a simple antiderivative to do. Equals. Again, I don't like the way that's written. Let's make it so I can do antis on this guy. And of course, the 1 is easy. So box 0 to 4. Your anti is u to the 1/2 divided by 1/2 minus the anti here is u, 0 to 4. Simplify this guy, pull the 2 out. Computer got slow there for a second. 2 square root of u, 0 to 4, minus, this guy is, let's go ahead and do this. It's 4 minus 0. You plug in the 4 minus the 0. And then down here you get 2 square root of 4 minus square root of 0 minus the 4, which is 2 times 2 minus 4. All that work for a big donut. We're going to hang on to 55. Let's get down to the last part here so I can get this done relatively quick for you. Total area is area, not area under. Not area under. So it's not just the integral of the function. So it's not. It's asking for total area. So basically what it's doing is is a total area is kind of like my total distance traveled. The integral would be my displacement. How far have I displaced? But when I'm asking for total area, it's kind of like total distance traveled. I added all my directionals. In other words, if I travel 7 in one direction and I travel 7 in the negative direction, I have a total distance traveled of 14. Okay, so that's kind of where this comes into play, total area. So in a sense then, total area is defined as the area of the curve from A to B, wherever the values they tell you to go, and then it's the absolute value of the y. Now we're not going to be able to integrate this. So what we're going to do is we're going to separate it into its parts, the above part and below part. So let's take a peek at this curve. This curve is a up parabola starting at -3. So it looks like this. Now let's define where these zeros are, because we're supposed to be finding the total area under the curve from -2 to 2. I conveniently drew them right there because I know where those zeros are. So let's find out where those zeros are real quick. Hey, add 3, divide by 3, x is -1 and 1. So these two values are -1 and 1. So this region here is a positive area. This region here is a positive area. This region down here, the area under the curve is negative, but we're going to have to make that positive. So I'm going to, based on my picture, you can't quite do math without having a visual. So I'm going to integrate from -1 to 1 the function 3x squared minus 3 dx. That number should be a negative number. I'm going to make it positive. So if I integrate that, and I'm going to try to do this relatively quickly because I think you get the process. I want to get to the point. The anti is x cubed minus 3x from -1 to 1. Plug in 1 is 1 cubed minus 3 is -2, minus, plug in -1, you get -1, plus 3 is 2, you get -4. So the area on the curve is -4, but we want total area, so we use 4. This region here is the area under the curve from 1 to 2 of 3x squared minus 3 dx, which gives you the same anti, which gives you the amount 8 minus 8 8 minus 6 is 2. Minus, plug in 1, you get negative 2. That area is 4. I hope I didn't make any mistakes in my arithmetic. 8 minus 6 is 2. Plug in 1 is negative 2. Okay, so that's 4. So I've got, so far, I've got this region here is 4. This region here is 4, which means that region is 4 by symmetry. So the total should be 12. Let me just double check my answer here. Of course, it's not in the book. You can check my notes on the PDF file. Okay, so that's it. I will hopefully you'll have this complete for tomorrow, and I can't wait to see you.